Limits at infinity, Part 1. Assume m is a positive integer and k is a constant coefficient. Then the ratio of k over x to the m will get smaller and smaller as x gets larger and larger. If instead x is getting more and more negative, you get the same result. The ratio is getting closer and closer to 0. For example, 100 over x. As x gets larger and larger, this ratio is going to 0. 8 over x to the 3. As x gets more and more negative, the ratio is negative, but it's getting closer and closer to 0. Negative 72 over x to the 5th. The ratio gets smaller and smaller. And 10 over x squared. As x gets larger and larger, the ratio is getting closer and closer to 0. So if we're looking for the limit of something like 2 plus 10 over x squared, we can know that both limits exist, and so the limit of the sum will equal the sum of the limits. We can separate the limits because we know that both limits exist. Now, 2 really doesn't care what x is doing. And so the limit of 2 as x goes to infinity, well, 2's just going to keep being 2. But 10 over x squared, that's going to 0. And so the overall ratio is getting closer, or the overall expression, I should say, is getting closer and closer to 2. If we look at the graph of this function, we can see that as x gets larger and larger, the graph is getting closer and closer to the line y equals 2. Now, we could have done the same thing with x getting more and more negative, and we would have actually gotten the same result. The expression is getting closer and closer to 2. What about fractional exponents? Well, if x is going to infinity, then the expression is going to 0. If x is going to negative infinity, keep in mind that you can't take an even root of a negative number. So we're only going to discuss fractional exponents. If x is going to negative, we can only discuss fractional exponents if the root is odd. So again, let's look at an example. Suppose we have 3x plus 2 over the third root of x to the 5th. Well, the first thing I would do is I would rewrite it from radical notation to exponent notation. Then what I would do is I would break up the fraction into two fractions and simplify. Once you do that, you can see that both limits exist and both limits are going to 0, and so your answer is 0. Again, let's look at the graph of it. As x gets more and more negative, the graph will be hugging the x-axis closer and closer. And as before, we could have had x go in the opposite direction. As x gets larger and larger in a positive way, again, the ratio is getting smaller and smaller. Now, when we have such a discussion as x going to infinity or x going to negative infinity, we are discussing what's called end behavior. We're asking ourselves, what's the end behavior of the function? We're not interested in what I call the muddy middle. So even though we can see that this function has a vertical asymptote at x equals 0, we're not interested in that when we talk about x going to infinity or x going to negative infinity. In that case, we're just interested in end behavior. Now you might have noticed or remembered something from your pre-calculus. You might be saying to yourself, isn't she just talking about horizontal asymptote here? And if you're thinking that, you're thinking the exact right thing. If a function is going to a value like L, as x gets very large and as x is getting very negative, then we say that the function has a horizontal asymptote. So all of your knowledge of horizontal asymptotes can be used for this section. In part 2, we're going to continue our discussion of end behavior and horizontal asymptotes. I look forward to seeing you then.